Hi, Mr. Dale here, talking to you about energy. This whole unit for the next couple weeks will be dealing with energy, what it is, how we measure it, what we can do with it, and trying to understand its nature. First, let's think about what is energy? If we ask a bunch of people, well, hey, what is energy? One word, if you talk to more literary folks, might be vim or vigor or elan even. These are all great words, probably not so applicable in a physics context. Other words you might get, let's see, electric. Very important. We use this every day. Even when the power goes out, that's a serious issue. We still have batteries. Other words that might come about would be nuclear. Definitely an issue there. Efficiency. Word solar. Energy from the sun. Hydroelectric. Geothermal. Joules. Watts. Not really a measure of energy as it turns out. It's power, which is related but not quite the same. Work might be something that we talk about. Well, in general, I'll cut to the chase here. If we talk to a bunch of people, and people have, these are some of the words that come up for us. Let's get back down to there. Let's go to the top there, sorry. Uranium, atoms, electricity, station, source, non-renewable. All these things are at different aspects of energy. We're going to start looking very detailed at small bits of energy. So this is Wile E. Coyote. I hope you guys are still watching these kind of cartoons. There's a lot of good physics in there, some bad physics as well. We'll try to guide you. Let's see. Wile E. has just been chased off this cliff by the Roadrunner. He's very far off the ground. Guess what happens next? Let's have a little closer look at this. You can probably guess what happens after he finally realizes that he is that far above the ground. Ouch. So let's think about poor Wile E. He is way up high in the air, not moving, just in the magic cartoons. He's not started to fall yet. And then eventually starts falling faster and faster and faster. And eventually he hits the ground. Energy all around. The main types of energy that we're going to be thinking about are, in fact, we can call them potential energy. Potential energy. And the other big guy that we have is kinetic energy. Potential, what is that? You may have been asked, to work up to your potential. It's a possibility. Something you might do. It's stored up. In fact, in a physics sense, this is probably what would serve you well to think about. It's stored. Not doing anything quite yet, but it's ready to go. Kinetic. There's types of sculpture called kinetic sculpture. Calder is a very important person who's made a lot of these I can see in airports and in different cities. Unfortunately, Syracuse doesn't have any. Kinetic, you might be described as hyperkinetic. Some of us may be. This is motion, moving. So that's the energy that an object has if it is in motion. There's other types of energy that we'll probably talk about, and I'll mention them, but we'll get a little more in detail later. But for now, let's concentrate on these two types of energy. And of course, here we go. This is a section from our reference tables for the Regents physics. Make sure we know this. This will help you a lot. Delta PE, delta, meaning a change in. Let's kind of focus in on that for just a sec. So we have delta P, change in potential energy, PE, equals mg delta H. M, not surprisingly, as you probably know already, stands for the mass of an object. G is the force due to gravity. And delta H, this is where the delta comes from, change in height. So the implication from this, if we're not really thinking about a change in height, we could maybe rewrite this as PE equals mgh. This is a little tricky because it depends on thinking about, well, where do you measure the height from? Feet above sea level? Right now I'm standing on the floor. In terms of the floor, I don't have a lot of potential energy. I'm about as low as I can get. However, I'm not at 0 feet sea level. So we got to be careful about from where we measure our height in this. So keep track. And the other, KE, that is potential energy. Let's think about that just for a sec. Again, we have mass. So that is important. The more mass of an object, the more kinetic energy it has. But only if it's moving. We have v squared. V is the velocity. How fast something is moving. And remember, velocity is a vector quantity, so that means we have to be moving in the same direction. And it's squared. So let's see, what if we're standing still? Our velocity is 0. Therefore, no matter how massive the object is, there's no kinetic energy. You have to be moving in order to possess kinetic energy. We have a couple other ones that are going here. We have W for work. We'll get to these later. This one I want to think about as well. And we're going to touch on this a little bit. ET, T for total. Total energy is potential energy plus kinetic energy plus Q, which is heat. And where do we usually get heat from? You can't see me, but perhaps you can hear me warming up my hands by rubbing them. F for friction. So friction is the most common way we generate heat, and this is Q. And we can think about what else does friction do to an object that's moving? It slows it down. So let's build on this a little bit. This is an equation that does not appear in your tables, but I think we've talked about it. You've certainly heard about it. Energy is conserved. What does that mean? If we conserve our natural resources or we conserve a park, it means that we keep it, keep or save. What this means is that the total energy has to be the same. It can't change. It can change from form to form. In fact, as Wiley, experienced there, he had a great deal of potential energy being, I'm guessing, 100 feet off the ground when he left the cliff. And as he went lower and lower, he's lower, so he has less potential energy. Where'd it go? Into kinetic energy, into motion. At the very end, all of a sudden, a little while after that dust cloud settles, we'll see that he's no longer moving. Where did that energy go? We can't lose it. It went to a big banging sound, certainly, sound energy, that's legitimate. And it also went into probably, well, not to be too grotesque, but probably breaking some of his bones, et cetera, although he seems to come through all right every time. So I'm going to expand this a little bit. And by the way, EF final equals E initial. That means a before and after, and how we define before and after is up to us. Now we can break this out. Well, what sorts of energies do we have? Let's think about Wiley. He had potential energy, and that was about it. To begin with, so he had his initial, and then at the end, he had a lot of kinetic energy. Now, so this is important. What is our initial and final situations, our states? So for Wiley, I'm going to say I have Wiley. While, I'll leave it as while, initial, hanging in midair. Wiley, final, just hitting the ground. And let's see, he's at a stop. So his velocity is 0. Well, let's kind of put this together. And we can do this with an equation. You know how I love equations. So we can say that, and I'm going to go with the final state. So at the ground, let's see. Well, let's see. Energy we said was from our equation before, that kinetic energy plus potential energy is the total energy. And I'm going to say that this is the final. And we're going to have kinetic energy and potential energy on the side again, except this will be the initial and the initial. So let's see, he's hanging in the air, so he's not moving. What does that mean for kinetic energy? It must be 0. So this part goes to 0. And what happens in here? Oh, right, we have that nice equation, mgh. Awesome. Now, just when he's hitting the ground, actually his velocity is not 0. I made an error here. Just when he's hitting the ground, he's moving very quickly. So his kinetic energy, well, recall, don't worry about that you don't have this memorized because you can use your tables. I always let you use them. And potential energy, well, he's at the ground. So his height relative to the ground is 0. So this part goes away to 0. So basically what we have now, which is kind of cool, is what started being kind of complicated is now mgh equals half mv squared. Let's see what else we can do with this. Well, that's kind of cool. We have an m on both sides. We can cancel them out. Excellent, this is even better, which is very interesting. So if the mass doesn't change, if the mass is the same on both sides, in general, it can cancel on both sides of this kind of calculation. At this point, I think you have enough to go and think about using some of the simulations that I have for you to answer some questions. As always, please feel free to stop me in the hall if it's a day that we don't have class, or during class, or email me if it's one of the many days that we don't meet. I don't want you to flounder online and struggle, so always get a hold of me and ask for help. I'm fairly obsessive about checking emails. All right, well, good luck.